Right, so I had a couple of requests to look into moments, and I had one from Mina George and one from MS Malik 36, so let's dive straight into it. Now, the very first thing we're going to need if we're examining moments, we shall need some form of pivot in a bar. There we go. Nice little yellow bar with a pivot on the left hand side. There's no reason for the bar to be yellow. You can make it any colour you want. So, there are two things that are very important when we're dealing with moments. Here we have a bar and a pivot. There's no moment acting on it. What we need is a force to act on the bar, and that force will have to be a distance from the pivot, specifically a perpendicular distance to the pivot. Okay, so let's start that now. So we have our pivot and our bar labelled, and we need our distance in our force. Now specifically, as we said before, this is a perpendicular distance to the pivot. Okay, so the moment is defined as the force times the perpendicular distance to the pivot. I'll talk briefly about what this means, a perpendicular distance to the pivot, and for the most part why it's not really important at this level. It becomes more important certainly as the next levels go up. For most of the forces that you come across, they'll be giving you the perpendicular distance to the pivot anyway. So I'll show you what that means. If I take my force and I was to draw a little right angled line to it, I'd find it would come out here and go straight through the pivot. There we are, that's my right angle. So let's give you an example of a situation where that's not the case, and just so you understand why most of the time it won't matter at all. Okay, so let's examine a situation where we've got a force which is not acting at that nice little right angle direction down there. So I have a force acting like this from the point. This is where the perpendicular distance becomes important. Perpendicular distance to the pivot. And what it means is we draw a right angle from the force through to the pivot. There we go. And this is the distance we're interested in. And that's why you'll very, very rarely come across it at this level. Most likely never come across it. So although you need to be comfortable with the definition, the moment is a force times the perpendicular distance to the pivot, it won't really be an issue until you start hitting AP level or IB level or AS level. Okay, so let's just get rid of that. And you can see now where the perpendicular distance itself comes from. And there we go, problem's gone away. Okay, so now we've got a situation, we've got a force and a distance. Force and a perpendicular distance to the pivot. Let's have a look at calculating the moment. Let's suppose this force over here is 12 newtons. And let's say the distance is 50 centimetres. Well, moment equals force times distance. That's 12 newtons times 50 centimetres. But I wouldn't write 50 centimetres. Why not? Because the units of moment are Newton metres. So it would be 12 newtons times 0.5 metres. So always want to convert it to metres. And that would give us a moment of 6 Newton metres. There we are, problem solved. That's a very basic calculation for the moment. Now, I've drawn a little clock in the bottom right hand side there. And that's just to illustrate that moments come in two types, and two flavours if you will. One is the type that tries to push objects round in the same direction as the clock hands are turning. And they're called clockwise moments. So a clockwise moment would try to spin things round in that direction. And an anti-clockwise moment would try to spin things round in the other direction against the clockwise moment. So an anti-clockwise moment. There we are. So they're the two different types. So why do we use them? Because it's pretty helpful to be able to categorise what type of moment things are. Now, there's a reason it's helpful. There we go. I've just drawn a little balance beam there, sitting on top of a pivot. Now, that beam will be balanced if all the moments trying to push it in this direction, the anti-clockwise direction or balanced by all the moments trying to push it in the clockwise direction. So if the anti-clockwise moments, all of them added together, are equal to the clockwise moments, then it will be stationary, it will be in equilibrium. And that leads us into something called the principle of moments, and that's a very important thing. The principle of moments says if an object is balanced or in equilibrium, then the sum of the clockwise moments is equal to the sum of the anti-clockwise moments about any point. I'm going to explain what that means. But first things first, let's just practice using it. So there we go, the principle of moments. If an object is in equilibrium, then the sum of the clockwise moments equals the sum of the anti-clockwise moments about any point. And let's start doing some examples of that. Alright, so there we go, we've got a little balance beam there, and we've got a pivot in the middle. Now let's draw in some forces and some perpendicular distances to the pivot, some distances to the pivot. So on the right, I have a force of 20 newtons, pushing downwards. And that's a distance from the pivot of 2 meters. So perpendicular distance to the pivot, 2 meters. From now on, I'm just going to say distance to the pivot. Okay, so the distance to the pivot of that force is 2 meters. Let's add in another force. There we are, mystery force F. You can feel the excitement building. And our mystery force F is 1 meter from the pivot. So distance is 1 meter to the pivot. Okay, so the question is, how big is F? So the first thing we're going to do is let's examine the moments that are being created. Oh, key point as well, in order for this to be used, this beam has to be balanced. Or in equilibrium. And of course, in equilibrium just means balanced. In this case anyway. So first things first, let's look at our clockwise moments. Now, don't forget our clock. There we are, throw a little clock hands there. It's going to be moving around in this direction. And the force which will move things in the clockwise direction here on my balance beam is the 20 Newton force. So the moment equals force times distance, which is 20 newtons multiplied by 2 meters, which is just 40 Newton meters. Now let's examine the anti-clockwise moments. So again, that's force times distance. In this case, we don't know the value of the force, it's just F. F times 1 meter. The key point here is that because everything's balanced or in equilibrium, the anti-clockwise moments and the clockwise moments must equal each other. So what does that mean? Well, that means that 40 Newton meters, which is the clockwise moment, must be equal to the mystery force F times 1 meter. And that's because the anti-clockwise moment and the clockwise moment must equal each other. There we are. So that 40 Newton meters equals the force times 1 meter. I can divide both sides by 1 meter. 40 Newton meters divided by 1 meter will give me a force of 40 newtons. And that is the force F. So what does that mean? Well, we were able to use this idea that they're balanced, that the clockwise moment and the anti-clockwise moment must equal each other to get a value for F here, which is 40 newtons. Alright, so let's go into that again in a little bit more detail. Let's look at some more interesting things that come out of that. Alright, so here we go. Here's another balance beam. Now I've got 10 newtons on the right hand side, a distance of 1 meter from this pivot point in the middle, and I have another mystery force F, 1 meter on the other side from that pivot point. Okay, now let's look at a slightly more honest example. The first example we looked at was quite interesting. We've got our pivot point, but the pivot was doing nothing. In real life, that pivot is holding up this balance beam. So there's forces acting from the pivot point. There we go. Let's put in a force of 20 newtons acting on that pivot point. Now, you could look at it straight away and you could say, hey, you know what? I know that force is 10 newtons. that's because I've drawn it, so it's a pretty straightforward example, and we're going to do some interesting stuff with it. But let's actually examine it. First of all, how do we prove it's actually got the value of 10 newtons? Because now we've got an extra force pushing upwards. So let's see it. So first things first, we've got our principle of moments. Our principle of moments stated that the sum of for an object in equilibrium, in fact we should label that, in equilibrium, very important. For an object in equilibrium, the sum of the clockwise moments is equal to the sum of the anti-clockwise moments about any point. And that has some interesting end results for us. So what we're going to do is we're going to select some point, some pivot point. The first one we're going to do, the most obvious one, we're going to select that pivot point here, the bit where it's touching the bottom of the balance beam. And then we'll look at the clockwise moments from there and the anti-clockwise moments. We're going to call this pivot point 1. There we go. So from 1. Let's look at the anti-clockwise and the clockwise moments. So looking at it, from that pivot point 1, then the clockwise moments will be 10 newtons times 1 meters, force times distance, and that's 10 newton meters. The anti-clockwise moments, well, again, force times distance, which is this mystery force times 1 meter. And what we know about this, of course, is that this force times 1 meter must be equal to 10 newton meters. So I can divide both sides by 1 meter. And what I'll get is that the force equals 10 newtons. Because obviously the 1 meters would cancel out. There we go. Like that. There we are. Now that's if I use that nice easy little pivot point there. But what if I don't? What if I say, you know what? I don't want to use 1. It's too easy. I want to use 2. In fact, actually, before we go any further, there's a third force on here, that 20 newtons, that we haven't used. And there's a reason for that. Let's look at the 20 newton force around pivot point 1. Well, let's look at the moment it's going to create. Force times distance. That's 20 newtons, and because it's on the pivot point, the distance is 0. So it creates no moment. No, the moment from that is 0 newton meters. That's why we didn't include it. So now I'm going to use point 2 as a pivot point. And I know what you're thinking, there's no pivot point there. Doesn't matter. Let's look at our principle of moments again. Principle of moments, if an object is in equilibrium, the sum of the anti-clockwise moments is the sum of the clockwise moments about any point. It doesn't say it actually has to be a pivot. And this has got some interesting effects to it. Here we go. About any point. So let's look at it about point 2. First of all, we've got our clockwise moments. That'll be the things moving in the same direction as a clock. So things which are moving around in that way. Clockwise moments in the same direction as the clock are given by, the only thing moving in that direction is the 20 newton force. So force times distance. That's 20 newtons multiplied by a distance of 1 meter. That gives us 20 newton meters. Now let's look at the anti-clockwise moment. Well, that's given by our force times distance, always. Our mystery force, though, is the only one pointing against the clockwise motion. Okay, so that's our mystery force multiplied to the distance, which is now 2 meters. 2 meters from pivot point 2. So that tells me that it's 2m times f. Now again, it's in equilibrium. How do I know it's in equilibrium? It's written up here. So the anti-clockwise moment must be equal to the clockwise moment. That tells me that 20 newton meters must be equal to 2 meters times this mystery force F. Divide both sides by 2 meters. And what's going to happen is I'm going to be left with 10 newtons is my force. So what you can see there is that despite using point 1 and then point 2, I got the same value for the force. But I want to do something. I want to do something here. I want to prove a point. And the point I want to prove is that this thing here is more interesting than it sounds. So let's look at it. We've got our basic setup. We've got a force, a space, 20 newtons going up, and then another space then of 1 meter and 10 newtons going down. So let's draw that out. We've got our force here going down, which is a mystery force. We've got our force here from the pivot in the middle pushing upwards, which is 20 newtons. We've got our other force on this side, which is 10 newtons pushing downwards. And what I'm going to do is I'm going to take as a pivot point somewhere unusual. I'm not going to take anywhere on here. Why would I? Too easy. What I'm going to do, I'm going to take a point over here. And this point, it's not even on the beam. This point is 99 meters away. That's pretty far. And I'm going to look at the clockwise moment and the anti-clockwise moment about this point, which is pretty much unrelated to the situation. And what I'm going to do is I'm going to show you that this is true. Because if it works out, I should find myself getting the same answer that I've already got on 2 different occasions. The force is 10 newtons. So here we are. I've got my pivot point 99 meters away from the first force of 10 newtons. Got my clockwise, my anti-clockwise moments. So let's look at that. My clockwise moments, the things that should make it move in the same direction as a clock. Well, if we've got force times distance from that point, which is 99 meters away, well, that's going to be 20 newtons is the one going clockwise, multiplied by a distance of 100 meters. Because don't forget, I'm just copying this down from above, so the same distance is involved here. We've got 1 meter here, 1 meter here, which is 2 meters in total between the start and the end. Okay, so that gives me a clockwise moment about that point of 2000 Newton meters. That's a lot of torque. Now let's look at my anti-clockwise moments. Well, I have 2 of them. The first one, force times distance. You know what? Force 1 times distance 1 plus force 2. Here we go. Times distance 2. Because this is what it means when it says sum of the clockwise moments. It's the sum of the anti-clockwise moments. It doesn't mean we're just taking some of them. It means we're adding all of the clockwise moments together, and we're adding all of the anti-clockwise moments together. Okay, so force 1 times distance 1. Well, what do we have? We have 10 newtons times a distance of 99 meters. Plus force 2 times distance 2. Well, at that point we have mystery force multiplied by 101 meters. Alright. So let's just continue that on. That's going to give me 990 Newton meters plus 101 meters times F. Alright. And they have to be equal to each other because the balanced clockwise and the anti-clockwise moment must be equal to each other. So that means that 2000 Newton meters must be equal to 990 Newton meters plus 101 meters times F, or mystery force. Let's come down a bit further. If I subtract 990 from both sides, then I'm going to get 1010 Newton meters equals 101 m, 101 meters times F. If I divide both sides by 101 m, then what I'm going to get, right, let's just do here, 101 m, divide that side by 101 m, then what I'm going to get is 10 newtons equals F. That's it. So what you can see is that, despite how it looks, is actually quite an interesting statement because of the effects it has. It doesn't matter where you pick the point as long as the situation you're dealing with is a balanced situation which is in equilibrium. Right, now what I'm going to do is I'm going to put in a question from one of the past exam papers. I believe this one's from 2018, and this was one that one of the students asked about. So let's put it up. We'll do a run through of it. This is the one from the video I've already put up, and then I'll talk a little bit more about things like centre of masses and the effects that that can have on moments. Question 2. Figure 2.1 shows a uniform plank, AB, of length 2 meters suspended from two ropes, X and Y. The weight W of the plank is 210 newtons, and that's labelled on there. The force in rope X is P. The force in rope Y is Q. State in terms of P the moment of force P about B. Alright. Well, what do we know? We know that moment equals force times distance. Specifically perpendicular distance to the pivot. But moment equals force times distance, so what do we have? So we want to find the moment of force P about B. Well, force P, that's the magnitude of it, it's P. And the distance is 1.5 meters from B. So here we are, force P, the distance between here and here is 1.5 meters. So that's just 1.5 times this value of the force P. So 1.5 P. Make sure that decimal point's nice and clear. Okay, let's look at the next bit. Calculate the moment W about P. Okay, so the moment of W about B. So let's find W. Here we are. W is the weight, and it's asking for the moment of W about B, so we want to know what this distance here is. W is from the centre of mass. It's the weight from the centre of mass or the centre of weight of the object, and it points directly down. What does that mean? Well, we've got a uniform plank, so it'll be in the middle. The plank is 2 meters long, so this distance here will be 1 meter. Alright, so the moment of W about B is just simply going to be 1 meter times 210 newtons. So force times distance, 1 meter times 210 newtons, and that will give me 210, oops, don't need an equal sign there, Newton meters. There we are. Now here we go, here I've got the units for moment, which is Newton meters. In fact, there you go, there's a reason why you have to be careful. State in terms of P, I didn't put the units in. Newton meters, make sure you're writing those units in. Okay, now calculate the force P. We know that when an object is in balance, the moment about any point has to equal 0. So what do we have? Well, the anti-clockwise moment must equal the clockwise moment. And if we look at our diagram, we're dealing with moments about this point here, which means that the weight W is anti-clockwise. It's an anti-clockwise moment, and force P up here is producing a clockwise moment. There we go. So they have to be equal to each other. That means that 210 Newton meters must be equal to 1.5 P Newton meters. Oops, capital N, there we are. So I divide 210 by 1.5 and I should get the value of P. There we go. Rearrange that for P. P is just 210 Newton meters divided by 1.5, which will give me a value of 140 Newton meters. And again, remember our units as we put it in. Part 3, the force Q. Okay, so we have to calculate the force Q. Let's look at that picture again. There we go. And what I'm going to do is I'm just going to erase a lot of the work I've put on there. There we go, and that should make it a bit clearer what I'm going to do. Okay, so we know that if it's balanced, then the clockwise moment and the anti-clockwise moment from any point should equal 0. And what I'm going to do is I'm going to calculate the clockwise and the anti-clockwise moment by, let's say I'm going to use this point in the middle, W, here. Why am I going to use this point? Because force times distance, 210 times the distance of 0, gets rid of that problem altogether. That just vanishes. So that gives me a clockwise moment and an anti-clockwise moment. This one here is a clockwise moment. This one over here suddenly becomes the anti-clockwise moment. There we are. Alright, So the distances, well this, that's 1 meter, this is 0.5 meters between there and there. So choose points about W. Right, now as we looked at that before, that was 0.5 times P on one side, and on the other side it was, looking for Q, it was 1 meter times Q. Now I've got a value for P. I've got 140 Newton meters. So 0.5 times 140 equals 1.0 times Q. In fact, I can rearrange that straight away and that'll give me a value for Q. The force is then 70 newtons. So the force from Q should be 70 newtons. Right, and I just want to review this because I know a few people have difficulties with this idea. You can take the moment from any point. And what I'm going to do is I'm going to take the moment from some different points to show that it still works out. Right, so suppose I didn't take them about this point W. Suppose I took them about point P. There we go, let's just erase the mess that's there at the moment. There we are. If I take them about this point P over here, it'll be actually about that point there, then my force times distance, I've got my clockwise and my anti-clockwise. This is clockwise, this over here is anti-clockwise, and we're doing it about P. So let's look at the different bits involved. My force times distance from P is P times 0. From this one, the weight would be 210 newtons times 0.5 meters. That's 105 Newton meters. And if I come all the way over to Q, then I have the distance from P is 1.5 meters, and I've got Q in newtons times 1.5 meters, and that has to equal this value over here. They have to be the same because my clockwise and my anti-clockwise has to balance. So that tells me that Q times 1.5 equals 105 Newton meters. I divide both sides by 1.5. That tells me that Q is 105 Newton meters divided by 1.5, which will give me a value of 70 newtons. This equals 1.5 meters. There we go. So I can take it from that point as well. But now, okay, what if I don't want to use either of those points? Will it still work? Let's look at it. I'll take this writing off the board. Now what I'm going to do, I'm going to go crazy. Let's use A as our point. Now let's look what we have. We have an anti-clockwise moment here, we have a clockwise moment here, and another anti-clockwise moment up at the end in Q. Okay, so I'm going to take moments about A. I know the clockwise and the anti-clockwise moments have to be equal to each other, they're just in the opposite directions. So what does that tell me? Well, let's look at the clockwise moment. So the clockwise moment is 210 newtons multiplied by 1 meter, which is how far it is away, and that gives me 210 Newton meters. That's how far away it is from A, that's 1 meter. So let's look at my anti-clockwise moments. So my clockwise moments are what, 210. My anti-clockwise moments over here are from P, and we worked out P, and P is 140 newtons upwards in this direction. There we go. I nearly said 140 Newton meters. Of course not, it's 140 newtons. Well, let's look at P first. It's 140 times 0.5 meters. That's newtons times meters, so that'll give me 70 Newton meters. And now I have another force from Q, which is Q multiplied by 2 meters. There we are. Okay, so let's look at that. 70 Newton meters plus 2 meters times Q, they have to be equal. So I just subtract 70 from both sides, and what I get is 140 Newton meters must be equal to 2Q, which means divide both sides by 2, and I get 70 Newton meters equals Q. Okay, so let's go down here and see we've still got the same answer. We tried it 3 different ways from 3 different points, but it really doesn't matter where in space you take it from. If you have your balance beam much the same as that, there we go, here, you could take your pivot point over here. You will still get the same answer. So it's just about picking the choice that's easiest for you. Right, so what I want to do now is briefly touch on this idea of the centre of mass. So first things first, centre of mass. What is it? Well, the centre of mass is the point about which all of the object's weight appears to act. Now, you can actually find the centre of mass of an object. When you deal with three-dimensional objects, it gets a bit more tricky for obvious reasons. But when you're dealing with an object that's only two-dimensional, or at least close enough to it, for example, a piece of cardboard, if you take a piece of cardboard, you can find the centre of mass of that piece of cardboard. And the way they tend to refer to that is they don't call it a piece of cardboard too often. They'll say something like two-dimensional lamina. So they refer to it as a two-dimensional lamina, and that's just the theoretical description of it. In reality, you're going to be dealing with a piece of cardboard in situations where it tends to come up. So let's just have a look at what happens with this piece of cardboard and how you find the centre of mass. Okay, so first things first, we start off with a square piece of cardboard, and what we would want to do is suspend it freely on one corner. So you put a pin in it, something where it's able to move around freely. And once it finishes moving around, what you do is you just hang, say, a piece of string down from it with a weight on the bottom. Make a couple of marks along the string, take it off, and once you've taken it off, what you want to do then is just physically, with a ruler and a pencil, draw in the line along that piece of cardboard. Then what you do is you take that piece of cardboard and you hang it from a different corner. Oops, my cardboard's going a funny shape now. Let's just assume it's still square. There we are. So hang it from a different corner. Here's the line I've drawn earlier, and repeat the process. Repeat the process. You hang down your little weight on a piece of string, and then of course you take that and you draw in the line that's actually made. Where those two lines meet, here, the centre point, this is the centre of mass. So now you've got the centre of mass of a cardboard, the centre of a sheet of cardboard. What can you do with that? Well, you can, using the superpower that you have now developed, take that piece of cardboard where it's marked in the centre and balance it on top of a pencil. Yeah, that's pretty much it. You can balance it on top of a pencil. Awesome. So why bother? Well, with the exception of having fun balancing on top of a pencil, what it does is it proves a concept. And it's this idea that really what's happening is when you look at one of these images, on the left and on the right, there's lots of, you can deal with it as lots of little strips if you like, each creating its own moment about the centre. In the anti-clockwise moment, the clockwise moment's balancing, and it's balancing along that line. And that line, somewhere on that line of course, is our centre of mass, and the same thing happens when you balance it from the other side. So that line coming down from the centre of mass is referred to as the line of action. And that's actually quite important. So that force line that comes down from the centre of mass, which is basically the weight of the object, that's what the force is, but the line itself is called the line of action. Now, when an object is balanced, which is where it comes back into obviously dealing with moments, when an object is balanced, what it means, if it's physically sitting on the ground, it means that the line of action of the object lies inside of the base, and that means it's pretty stable. If it lies outside of the base, it will fall over. So this line of action is related very strongly to the stability of an object. And there are three types of stability. Alright, so our stability relates to equilibrium. That idea that it's not moving. So we get stable line of actions inside the base, and that's called stable equilibrium. Unstable line of actions just inside the base, so I'll draw a picture of that to try and make it a bit clearer in a second, and that's unstable equilibrium. And neutral equilibrium, slightly different setup. Let's show you. So stable equilibrium, we have a square. The square has centre of mass, the line of action is very clearly in the base. If you move that square, nothing is going to happen. In fact, nothing will happen right up until you have your square on a 45-degree angle, and then suddenly it becomes unstable and it will fall over. So if you try and move it, if you try to lift it up, what will happen to our square is it will just fall back down. Okay, so let's look at unstable equilibrium. I take a triangle, I balance it on the tip. Yep, that's not very stable, not very safe, it's not going to hang around for long. So we have a line of action there, just inside the base, but you know what? It's going to fall over. Maybe just inside the base, but the base is so pointed or it's so unstable, it's not going to last for long. Now neutral equilibrium. So what's happening in our first two setups? We get stable equilibrium, unstable equilibrium. Stable equilibrium, when we try to move it, when we try to tip it over or move it, the centre of mass moves upwards. It has to. Centre of mass has to increase in height, so it takes energy to move it. Unstable equilibrium, the centre of mass moves downwards if it moves. If it starts to fall over, the centre of mass goes down. So this first one, stable equilibrium, takes energy to move. Unstable equilibrium, the moment it moves, it gives out energy. It's got that increase in kinetic energy because of change of gravitational potential energy. Neutral equilibrium, the line of action of centre of mass doesn't move. Neutral equilibrium centre of mass doesn't increase in height, it also doesn't decrease in height. And when does that happen? Well, when we get a ball. You can move it, and it's just going to roll and then stop moving. That's fine. It's not stable, it's not unstable, it's neutral. You put it on a flat surface and it will just stay there till you move it. Okay, so the key point to all of that is this idea that the centre of mass is a point about which the force, or the weight, appears to act. And it acts down that sort of line of action. It's very important in terms of stability. In fact, the key point here is another definition that you need to be aware of when you start dealing with these kind of things, is that an object is stable if it has a low centre of gravity or centre of mass and a wide base. There we are. So an object is stable if it has a low centre of mass or centre of gravity and a wide base. Now at this point some of you are probably saying, centre of mass, centre of gravity, what's the difference? There isn't one. There just literally isn't one. Centre of mass, centre of gravity are the same thing. Okay, so now we know this, we can start looking at some slightly more curious sort of effects for moments. Now let's pull one up now and do a calculation. There we go. What I've done is I've drawn a little balance beam, and in true style of what we know now, I have to write that the beam is balanced. There we are. We get a pivot, which is 10 centimetres from one end. One end has a 10 Newton force acting on it. The beam is 1 metre long. And the question is, what is the weight of the beam? Alright, so straight away I can look at this and I can jump in, I can start calculating the weight of the beam. I'm going to take our pivot point as the pivot. So let's do that. We want to look at our anti-clockwise moments and we want to set them to our clockwise moments. Now, for our anti-clockwise moments, we have force times distance, and that equals 10 newtons times 0.1 meters. So that gives us 1 Newton meter. And that has to be equal to the clockwise moment. So force times distance. But wait, where's the force? Well, I'm glad you asked that. Does this mean we can't do it? Do we have to stop? Do we go home? Put our feet up? Have some cheese? No, we don't do that. There is a force acting on the right hand side, and that force is from the weight of the bar. So there's a force due to the weight of the bar. Where does that force act? Well, that force acts as if it's from the centre of mass, which, as we know, is 50 centimetres in. If we get a 1 metre bar and it's nice evenly spaced, then it's going to be force due to the weight of the bar is acting at the 50 centimetre mark, which is 40 centimetres from the pivot. Okay, so now we can start jumping through the rest of our section. We have force due to the weight of the bar multiplied by 40 centimetres, 0.4 metres. Now, I can take these points, 0.4 metres times force due to the weight has to be equal to 1 Newton meters. So if I divide both sides by 0.4 meters, and that will give me a value that the force from the weight of the bar is equal to 2.5 newtons. Awesome. So by just balancing the beam at one point, we were able to find the value of the weight of the beam. There we go. That's actually pretty cool. And we were able to do that because the centre of mass, the centre of gravity, is this point about which the entire weight of the object appears to act. So there we go. Let's look at another one. There we are. So we've got a tractor and a trailer, and we're being asked to find values for F1 and F2. We've got trailer, which is a weight of 120,000 newtons. We've got F1 and F2, a couple of distances, and nothing else. And I tell you what we're going to do. We're going to find values for F1 and F2. And we're going to use this idea that we can take the moment from anywhere. Where are we going to take moment? We're going to take moment. First one, let's use point F1. Why? Because then we've only got F2 times distance and weight times distance. Because F1 times distance is 0, because the distance to F1 from F1 is 0. So we'll just choose F1 as our first point, and we'll look around that point. So choosing moments about F1. Well, what does that give us? We have our clockwise moments equal to the anti-clockwise moments. And our clockwise moment is 120,000 newtons. Force times distance, which is 4 meters. And that has to be equal to the clockwise moment, which is mystery F2, multiplied by the distance to F1, which is 6 meters. Alright, so let's work that out. That tells us that 6 meters times F2 equals 480,000 Newton meters. So F2 then is given by 80,000 newtons. There we are. So F2 is 80,000 newtons. Suddenly I've got a value. Awesome. Let's look at choosing moments about F2 this time. So again, we start off with this situation. Our clockwise moments have to be equal to our anti-clockwise moments. So let's look at our clockwise moments. Well, that's the only one going clockwise when we're looking from this point over here, F2. The only thing going clockwise is F1. So F1 times the distance of 6 meters has to be equal to, there we go, we've got our weight, 120,000 newtons. It's pretty big. Multiplied by the distance of 2 meters. Wow, so there we go. F1, 6 meters times F1 is equal to 240,000 Newton meters. Divide both sides by 6 meters, and what I'm going to get then is F1 actually has a value of 40,000 newtons. There we go. I've actually got values for F1 and F2, and it gets better than that. Look, what I'm saying is I have a weight acting downwards of 120,000 newtons. Well, let's look at what I have acting upwards. Upwards over here, I have 40,000 newtons. Over here, I have 80,000 newtons, which means if I add all the forces going up and all forces going down, I've got 120,000 newtons going down, 120,000 newtons going up. So it's in equilibrium. There we are. So a little bit of fun there. So one thing I want to have a look at very briefly is cranes. Let's quickly draw one. So here we go, another type of question that comes up semi-regularly actually. Is this, what's the maximum weight the crane can hold? It's either this question or a type like it. And the idea being you can move that 40,000 Newton weight on the right hand side forwards and backwards closer to this central pivot point and as far out as 10 metres. On the left hand side you've got a hook which is 40 metres away. And of course the bigger the weight that you're lifting, the further over you move the 40,000 Newton weight so that it's best able to balance it. So the question is, what's the maximum weight the crane can hold, assuming it's completely balanced? So what is the maximum force? And it's actually just a nice straightforward question. What we have, again, is our clockwise moment or anti-clockwise moment, and the maximum weight is a situation where it will be balanced, and the 40,000 Newton weight is as far over as it can go. So our anti-clockwise moment has to equal our clockwise moment. We've got our force times distance on both sides. So our anti-clockwise moment will be 40 metres times max force. And that will have to be equal to 40,000 newtons, force times distance, times 10 metres, which is 400,000 Newton metres. That's 40 metres times our maximum force. And I can find the maximum force by dividing both sides by 40 metres, and in fact that will drop down and give me straight away 10,000 newtons. There we are. And that's our workman crane, the maximum that particular setup can hold. Excellent. So I hope you found that really useful and hopefully quite helpful. If you have, please feel free to like and subscribe. And if you want to leave any comments, leave them down in the section below. You know what? You have a great day.